So now we come to a new topic, which is Lebesgue's differentiation theorem. As the name suggests, this differentiation theorem relates the concept of derivative with Lebesgue's integration theory. And now we restrict ourselves to the case of the Euclidean space RD, and then we will see that from classical calculus we know that a derivative is an inverse process of the integral and vice versa. So Lebesgue's differentiation theorem generalizes this so-called first fundamental theorem of calculus for absolutely integrable functions. So let me put the salient features of Lebesgue's differentiation theorem. So first is that it relates derivative or differentiation with Lebesgue's integration theory. So on RD, now we are back to Euclidean space. And secondly, it generalizes the first fundamental theorem of calculus. So we have learned this in Riemann's integration theory, that the derivative of an integral is again the original function. So roughly, that the derivative is a left inverse to integration. So we will make these things precise, and then it also deals with a number of other differentiation theorems. So these differentiation theorems give criteria for functions to be differentiable outside of a null set. So differentiability almost everywhere for various classes of functions. So of course these three salient features make up quite a large number of results actually, and to go into the depth of each result would not be possible due to the lack of time, and in fact we will be only be concerned with this topic for the rest of our course, and this will be the last course for this topic as well. So let us see how Lebesgue's differentiation theorem generalizes the first fundamental theorem of calculus. So let me recall what is the notion of differentiability and what is the first fundamental theorem of calculus for differentiable functions. So let us look at the definition of differentiability of a real valued function defined on a compact interval in R. So this is differentiability in R. So we fix a compact interval AB. So here both A and B are finite numbers, real numbers, and we consider a function f from AB to the real line. So this function is called differentiable at a point x in AB if the following limit exists. So this limit is denoted by f prime x if it exists, and this limit is given by the fy minus fx over y minus x when y approaches x, where y is through any sequence of points in the interval AB minus this point x. So when this limit exists, if f prime x exists, we call it the derivative of f at x. And if f prime x exists for all x in this interval a b, it is called everywhere differentiable. And finally, if f prime x exists for x in AB almost everywhere, so outside of a null set in AB with respect to the Lebesgue measure, then f is called differentiable almost everywhere. And finally, one more terminology is that if f prime x is continuous, then f is called continuously differentiable. Continuously differentiable. So again, either everywhere or almost everywhere, depending on the context. So we have these terminologies, and now we are ready to state the first fundamental theorem of calculus. So now let's look at the statement for the first fundamental theorem of calculus. And it says that if you take again a finite interval in R, AB, and you take a continuous complex valued function f and define capital F, so you first take small f to be a continuous function and define capital F as the integral of this function f from a to x. So this here is a Riemann integral because it's a continuous function, so on a compact interval, so the Riemann integral is well defined. And so for any x in AB, you can define this function, which is the Riemann integral function for small ft. And now the statement for the first fundamental theorem says that now if you differentiate capital F, then you should get back the original function small f. So in fact, capital F is a continuously differentiable function on the entire interval AB. So it's everywhere differentiable, so it has two parts. So first is that f is everywhere differentiable on AB. So this is the first one, and the second one is that f prime x is continuous everywhere on AB. So it's continuous at all points of AB. So this is what we mean when we say that capital F is a continuously differentiable function on AB, and with the derivative f prime x, first of all, that it's a differentiable function, so the derivative exists everywhere, and the derivative is precisely the function small f that we began with here, and this is true for all x in AB. So this is the first fundamental theorem of calculus, and this is exactly what I mentioned before, that the derivative, so informally, so the derivative of the integral is the identity transformation on functions. So I'm just putting it in quotes. So if you view these integrals and derivatives as operators, which takes a function and gives you back another function, then the derivative is the left inverse. So this implies that the derivative is equal to the left inverse of the integral. So this is what we mean when we say the integral is an antiderivative it is precisely in this sense that it is the left inverse of this integral. Now there also exists a second fundamental theorem of calculus which gives you sufficient criteria for the integral to be a left inverse for the derivative, or the derivative to be a right inverse for the integral, which we will come to later. So this is the first fundamental theorem of calculus, and so let's look at a quick proof for this theorem. So let's look at the proof of this theorem. So we have to show that for any x in a, b, with a included and b excluded, we have that limit as h tends to 0 plus fx plus h minus fx over h is equal to fx. Noting that here we can only approach a from the right, so it's a right-handed limit with h approaching 0 from the right. Similarly, for any x in a, b with a excluded and b included, we should have that the limit as h tends to 0 minus, so from the negative side, approaching 0 from the negative side, fx plus h minus fx over h is equal to fx. So we have to deal with these two situations differently, because we have endpoints a and b, and one can only approach a from the right and b from the left. So let's denote the first equation as 1 and the second equation as 2. So I'll just prove 1 and the proof of 2 is similar. So to show 1, we note that fx plus h minus fx over h is equal to the integral from x to x plus h ft dt over h. So this is for any h positive sufficiently small and x in AB. So rather I should first write for any x in AB, and h positive sufficiently small, because h the magnitude of h will depend on x, because we need to have this integral defined for values of x between a and b. So h should be sufficiently small depending on the value of x, so that x plus h is not greater than b. Similarly, to show 2, we can say that fx plus h minus fx over h is equal to the same thing, but we would rather have x plus h to x ft dt for h less than 0, again for any x in AB with a excluded and b included, and h less than 0 sufficiently small. So now we can rewrite the first one. So for 1, we can write the integral. So remember that here h is positive. So from the integral from x to x plus h ft dt can be written as integral 0 to 1 f x plus h t prime dt prime, and even we can have a 1 over h here. So this is by a change of variables. T prime is t minus x over h, so that so first of all dt prime equals 1 over h dt, and t prime goes from 0 to 1 because t goes from x to h. So here we have a change of variables and a new integral from 0 to 1, and with the function f x plus ht prime dt prime. So we are going to use the continuity of f. So since f is continuous on AB, given x in AB and epsilon greater than 0, there exists a delta positive such that 0 less than h less than delta implies that f x plus ht prime minus fx is less than epsilon for all t in 0 1. So this follows from the continuity of f at x. So this means that in turn that the function, if we define a function gh for h positive and sufficiently small from 0 1 to c, given by ght as f of x plus ht, or rather t prime, let's say, then gh converges, ght prime converges to fx as h tends to 0 uniformly on t in 0 1, because if you go back to this, then this delta that is chosen does not depend on t and only depends on x. So its convergence is uniform over t in 0 1, and so this implies that the limit as h tends to 0 plus integral 0 to 1 ght prime dt prime is equal to the integral 0 to 1 limit h tends to 0 plus, passing the limit inside the integral now, dt prime, because it is a uniform convergence. So you can, for Riemann integration, you can interchange the order of limit and integration, and this is nothing but integral 0 to 1 fx dt prime, and this is just fx. And similarly you can prove, so this is, remember that gh was defined for h sufficiently small and fixing an x in AB. So here we have already fixed an x in AB and then chosen our delta and our h, so that you have a uniform convergence of these functions gh t prime as h tends to 0. They all converge to it converges to fx. So we have this for the positive side, and similarly one can show that limit h tends to 0 minus 0 to 1 gh t prime dt prime is equal to f of x. So this shows that the function capital F is continuous, and that the derivative of the continuous function f capital F is simply small f of x. So from the proof, we obtained this following corollary, which is called differentiation theorem for continuous functions, and it says that if f is a continuous function on a compact interval with values in the complex numbers, then we have that the limit from h going to 0 from the right side 1 over h, the integral of f over the interval x to x plus h is exactly f of x. This is for all x in AB where A is included and B is excluded. Similarly, the limit as h tends to 0 plus 1 over h, and then now the integral is over x minus h to x ft dt is again fx, and now this is for all x in AB where B is included and A is excluded. And if you combine these two, we get that the limit as h tends to 0 from the right 1 over 2h and integral over x minus h to x plus h of ft dt is again fx. This is for all x in the interior of the interval AB. And so this is the differentiation theorem for continuous functions that one learns in classical calculus. And the Lebesgue differentiation theorem can be seen as a generalization of this formula, for example. So Lebesgue differentiation theorem generalizes this formula for f when you no longer have a continuous function, but f is in L1 of AB with the Libid measure. So it's an absolutely integrable function on this compact interval AB, and this formula holds for x almost everywhere in AB. So this holds only outside a null set in AB. So we will see a proof of the differentiation theorem in dimension 1, which is for the real line, and then we will see also its generalization to higher dimensions. But for both these, we will need the so-called Hardy-Littlewood maximal inequality, which gives us the required technology to prove this Lebesgue differentiation theorem, which we will see now. So let's see the statement of Lebesgue differentiation theorem in R. So it says that if you have f from R to C, now we are no longer confined to a compact interval as before, because we are in the Lebesgue integral setting. So we are free to choose unbounded domains, and so we choose a function, complex valued measurable function, which is absolutely integrable over R. And now we define this capital F function as before, which is the integral of ft over the interval minus infinity to x. And this is now a Lebesgue integral. And now the statement, the assertion of the theorem is that f is continuous. This is the first part. And secondly, it is differentiable almost everywhere in R. So it's differentiable for x outside of a null set in R. And finally, and probably most importantly, that the derivative of x, derivative of capital F at x is equal to f of x for almost every x in R, meaning that this holds for x outside of a null set in R. So note that we have relaxed our assumption that f be continuous, and now we only consider absolutely integrable functions. But now our assertion is also weaker than before, because we are only asserting that this formula for f prime x, capital F prime, being equal to fx, this holds for almost every x in R and not everywhere in R. So a simple example will show that if you try to enforce f prime, capital F prime x to be fx everywhere in R, then this will easily fail. So let me give an example where, so this is an example for which f prime x equals fx for all x in R fails. So we can take f to be the function, the indicator function of the interval 0, 1 in R. So this is again a absolutely integrable function. F belongs to L1 of R, and so now we can try to deduce what is capital F. So capital Fx is by definition the integral. So this is by definition the integral of fx ft dt over, so I'm writing dt, but it's the same as dm with the Lebesgue measure. So this is over the interval minus infinity to x. So if x is less than 0, then of course then f is 0, because it's the indicator function, and therefore this is going to give you 0. Now if 0 less than or equal to x less than or equal to 1, then one can easily compute that capital F of x is simply x, because this characteristic function of 0, 1 is integrable, because 0, 1 is Jordan measurable. So it is Riemann integrable, and so the integral of minus infinity to x ft dt, so if x belongs to 0, 1, then this is equal to 0 to x ft dt, and this is nothing but x, because this is just the indicator function of 0, 1, so it's equal to 1 on this range 0 to x. So this is simply x. And now if x is greater than 1, then fx is nothing but 1. So the graph of small f from 0 to 1 is simply this function, which is 1 on 0, 1 and 0 outside. But so this is f of x, small f of x, but for capital F of x it is 0 outside for values of x between minus infinity and 0, then it becomes x in the range 0 to 1, and then it becomes 1 outside. So we can see that f of x is continuous, but not differentiable at x equal to 0 and x equal to 1. And so we cannot speak of so f prime x even does not exist for all x in R. So this example shows that we cannot hope to have the same result as before, where f prime x existed for all x in a compact interval AB, and it was equal to fx. So here this fails, but we still have the fact that fx is continuous. So we can easily show. So this is the first part of the theorem, proof of the fact that capital F is continuous on R. So how do we prove this? So this is easy, because if you write fx as the integral of f times the indicator function of minus infinity x dm, then if you take any sequence xn converging to x in R, then fxn, so let me write this as fn of x, which is fxn, and this is integral over R of the indicator function of minus infinity to xn. And so we have to show that fxn converges to f of x, and this is not very difficult because we can use the dominated convergence theorem. So using the dominated convergence theorem, so for the sequence of functions fnx defined by f times the indicator function of minus infinity xn, then we have mod of fnx, which is mod of fx times indicator function of minus infinity xn, and this is less than or equal to mod of fx, and this is an integrable function. So this implies that by dct we have f of xn, which is, so the limit as n goes to infinity, f of xn, which is the limit as n goes to infinity of the integral over R f chi minus infinity xn dm, and this is equal to the limit taken inside the integral of the function that you get when you take the limit inside f of chi minus infinity xn dm, but this is nothing but f of chi minus infinity x, because xn converges to x, so the indicator function of minus infinity xn converges to minus infinity x, and so this is nothing but the integral minus infinity x f dm, and this is exactly f of x. So we see that f is continuous. F is continuous. So this proves the first part of the Lebesgue differentiation theorem. Of course, the most difficult part is to show that f prime x equals fx almost everywhere, and for that we need some more technical results, what are called the Hardy-Littlewood maximal inequality, which we'll see in the next lecture.